Hi there, Rachel Chase here, and in this video we will explore calculating confidence intervals estimating population means when our population standard deviation is unknown. In the real world, this is actually much more common than what we saw earlier in the previous video regarding when you have an estimate for the population standard deviation. Those situations only usually occur if you're using historical data or something published by perhaps like a federal agency or something like that to estimate what's happening. So when we say population standard deviation is unknown, that means sigma unknown, but this does mean that we have the sample standard deviation instead. So earlier we were using population standard deviation, now we're using our sample standard deviation. The margin of error formula is almost identical. However, instead we use our t-distribution. And I'll take a few moments to explain what this means. You'll notice the equation is the t-score times standard deviation over the square root of n. Now, sample standard deviation is still in the same location. Nothing's really changed on that front. But what on earth is this t-distribution? Well, any type, if you recall back to chapter 6, any type of normal distribution is referred to as, and this part you may not be familiar with, a Gaussian distribution. That's not something you have to know. It's not something I'm asking you to memorize. But what that means is any type of distribution with that bell-type shape to it, all of those technically are different types of normal curves. Now, specifically, we learned about the standard normal distribution. What we use non-standard normal distributions for, in other words, all of those other types of normal distributions, are things that are based off of your sample size. If you look in your formula packet, you have an entire table dealing with your t-distribution. So this is the t-distribution of critical values. And on this table, you'll see a bunch of information, but it's all based off of what we call degrees of freedom, and then the area in the tail. You can also use your graphing calculator to get these values, so don't fear if you're having trouble wrapping your mind around this. It is just based off of two things. Degrees of freedom is calculated as n minus 1. So anytime you hear degrees of freedom, immediately calculate what n minus 1 is equal to. Each number on here, you'll notice instead of these being areas, these are the actual t-scores. So your area, based on the confidence level, is dictated above. And then with degrees of freedom, which is based off of your sample size, you can come up with your t-score. So what are the requirements of using this formula as opposed to the other one? If you remember from chapter 6 when we talked about the central limit theorem, your sample has to either be over 30, so greater than or equal to 30, or it can be under 30 with the announcement that the data is approximately normal. So these are the same regulations when we talked about central limit theorem. Let's take a look at an example. We'll do one by hand, and then we'll look at the next one using the calculator. A tire manufacturer wishes to investigate the tread life of its tires. A sample of 40 tires driven for 50,000 miles revealed a sample mean of 0.32 inches of tread removed. Construct a 95% confidence interval for the population mean. Would it be reasonable for the manufacturer to conclude that after 50,000 miles, the population mean tread remaining is 0.3 inches? So it's a two-part question. First part, construct your confidence interval. Second, see if that value seems feasible based on what they tell you or what your confidence interval is. So in our sample of 40, we found a sample mean of 0.32 with a sample standard deviation of 0.09. The trick here is to identify when they say standard deviation, if they're not announcing that this is population standard deviation, and more specifically, you see that they specify the standard deviation immediately after talking about what the sample mean was, and in that sample of 40, so all of this, it's more reading comprehension. All of this data is about your sample of 40. That's what indicates this is a sample standard deviation. Our confidence level is 0.95, so that means that alpha is 0.05. Now, please keep in mind, alpha is always the area in the tail regions. And I say this because based on alpha is how you calculate your t-score in this case. One other piece of information we need is if our sample size is 40, then how many degrees of freedom would that be? 40 minus 1 is equal to 39. So to find our t-score, so that is t of alpha over 2, if you will, 0.25. We go to our table and look up 39 degrees of freedom, which is way down here. And then if you look at the top, it gives us area in one tail versus area in two tails. Technically, if alpha is the area in the tail region, and this is split over both sides, that means there's 5% in both tails. And if you look above it, that matches what we got when we divided it by 2. So you're going to look for where those match up. What we'll end up using the one-tail stuff for is when we get into Chapter 8, looking at hypothesis testing. So if we take that area in two tails and go down to 39 degrees of freedom, we get a t-score of 2.023. From here, it's the exact same calculation that we did earlier. We plug in for our margin of error, 2.023, times our standard deviation of 0.09, divided by the square root of our sample size, which was 40. And this gives us 0.029. Next, to get your confidence interval, take your sample mean, 0.32, and add and subtract the margin of error. This gives us, when we subtract, 0.291, which is our lower bound, and when we add, 0.349. So we can be, according to this, 95% confident that after you drive 50,000 miles on those tires, there should be somewhere between 0.291 and 0.349 inches of tread remaining on those tires. So the second part of this question said, would it be reasonable for the manufacturer to conclude that after being driven 50,000 miles, the population mean amount remaining is 0.3? If that number fits within the interval that you've constructed, that would be a reasonable conclusion. So since 0.3 fits in this interval, we can say yes, this is in fact reasonable to conclude. If you prefer, and we can do this for the next example, if you prefer to use the calculator to acquire your interval, then you can use the t-test function, I'm sorry, not the t-test, the t-interval function, which we'll look at in the next example. A simple random sample checking the speed on I-95 near exit 4 is conducted using a radar gun on a Saturday afternoon, and it's found that the data is approximately normal. The new speed limit on the road is 65 miles per hour, and Del is curious to find out how travelers are reacting to this. Using the data below, construct a 98% confidence interval for the population mean. What might this suggest about that new speed limit? So the first thing you see is that we have a set of data here. Immediately, if you have a list of data, please put that into your list function and then use one of our stats to calculate your mean and standard deviation. There is another pretty cool function. If you're using the t-interval function, that will save you some time here. If you're doing it by hand, this readout will give you your sample mean and your sample standard deviation. So these would be the two things that you need. If you wanted to use the calculator to find your t-interval here, and also you could do that to get your margin of error, go to Stat, Tests, and scroll down until you find your t-interval. Anytime you have to calculate data like this, make sure if it's a sample set of data like we have here, this is not the only number of drivers going, right, that you're using your sigma unknown situation. So we have our t-interval, and we already have our data in list 1, so you'll notice it pre-populated this information for us, but what you could do instead is you could also tell it that you put this in list 1. So that's an option. Really, whichever one makes you happy, it doesn't matter which you use. Stats, if you did not already have a list of data and you had something like the previous example, you would have to use that function. So we can go back over that in a moment. So since we're using our data in what I put as list 1, leave frequency as 1 as a placeholder. Our confidence level we said was 0.98. When I calculate, this gives me my interval. And then from that interval, if we wanted our margin of error, we could do what we did earlier. Subtract, you have 60.653, oops, did that backwards, 71.514 minus 60.653, and then divide that by 2. This gives us the margin of error when you're using the calculator for that. So really, whatever option you'd like to go about, just make sure that you understand how to calculate the margin of error if you are using the interval function. So you can say that our population mean is somewhere between 60.653 and 71.514 miles per hour, and our margin of error is equal to 5.4305. So we are 98% confident that the population mean falls between these two numbers. What might this say about the new speed limit? Well, the new speed limit is 65 miles an hour. Does 65 fit in this interval? If so, that means that perhaps people are picking up that the speed limit has changed and things are working well. So that's really our interpretation side of things. The last thing to go over in this video is let's go back to the previous example so I can explain a little further how you would use your t-interval function if you prefer here. If you wish to use the t-interval function on this, you still can. However, this time you have to tell it to use stats, and it's up to you to enter that information. We have a sample mean of 0.32, a sample standard deviation of 0.09, and our sample size here was 40. In this example, we wanted to be 95% confident, and you'll see here that we end up with the same information on our readout. So what was our margin of error? 0.291 to 0.349 when we rounded. I'm sorry, not the margin of error, the interval. And then if you did the same thing and divided, you would get approximately 0.029 as your margin of error as well. Whichever you prefer doing, it's entirely up to you. Just keep in mind you have to show as much work as you can or as much work as you feel confident in, at least to potentially earn partial credit if you make a mistake. So the choice really is up to you on that front. Stay tuned because in the next video we'll look at how we can also apply this information to calculating confidence intervals when we have qualitative data such as proportions. See you there.